Imagine a universe without a grid. No axes, no ruler, no background canvas of space and time, just isolated events. Our intuition usually insists on placing these events onto a pre-existing stage, a framework where coordinates and distances are already defined. But to see the structural skeleton of the universe, we have to throw that stage away and build from scratch using only primitive logic. A quantitative distance answers a metric question: how far apart are these two objects? But an order answers a relational question: can this event influence that one? We can model this using a set of events E, equipped with a single rule: causally precedes. Causal order alone acts as the skeleton of reality. It organizes events and rules out physical possibilities before a single ruler or clock exists. This web of influence is governed by a strict partial order. The first axiom is irreflexivity. Physically, this means an event cannot cause itself or exist in its own causal past. The second axiom is transitivity. If X precedes Y and Y precedes Z, then X precedes Z. Causal influence chains forward across events without breaking. Finally, the order is not necessarily total. Two events can be incomparable, meaning they have no connecting arrows at all. This incomparability is the mathematical expression of space-like separation. It allows the causal structure to account for events that can never influence each other. Consider four events: A, B, C, and D. Arrows flow from A to B, A to C, B to D, and C to D. Transitivity reveals a central connection from A to D, creating two parallel chains. Yet B and C have no connecting arrow. Because B and C are mutually incomparable, they are completely causally unordered relative to one another. This configuration, one cause influencing two incomparable events that eventually influence a final event, forms a causal diamond. It's a fundamental geometric building block of spacetime. But these diagrams trick our visual biases. The ink on the screen creates an illusion, as if the drawn lengths and angles were physical facts. Even as the layout warps and the apparent physical lengths stretch, the topological arrows and causal comparabilities remain invariant. To see the danger, consider a causal chain with exactly 3 links and place a ruler over it. The assumption that 3 visual links equal exactly 3 units of physical distance is invalid. This is metric smuggling. Chain length is an order-derived combinatorial quantity, not a spatial measurement of proper time. Turning an order into a physical distance requires a specific model, a scale, and sampling data, choices that the order alone does not provide. If order doesn't determine distance, how do we recover spacetime geometry? The causal set program solves this by treating the discrete set as fundamental. In this hypothesis, the causal order provides the conformal structure, effectively the boundaries of the light cones. Then, local finiteness, the discrete counting of events, supplies the missing volume information. Causal order plus volume data can recover geometry, but an arbitrary partial order on its own is not a faithful metric space. Return to the 4-event causal diamond. To reach the next level of the theory, we have to change what we define as the basic point of our geometry. Instead of focusing on individual event points, look at the entire extended region between them. Mathematically, this is an order interval, the set of all elements sandwiched between a specific past and future. Now we collapse that volume. We are going to treat the entire interval as a single fundamental mathematical unit. This is a change in coordinates. Causally complete regions, rather than point-like events, are now the baseline of the space. By mapping different causal diamonds to individual points, a new auxiliary geometric shape begins to form. Treating extended regions as points allows for the construction of a geometry entirely distinct from the original spacetime. The formal name for this region-based geometry is kinematic space. Kinematic space is used in advanced holographic constructions, particularly in ADS-CFT models. It organizes information by extended intervals, tying boundary entanglement data directly to the geometry of the bulk spacetime. But while this is established in continuous holography, it marks an unsolved frontier for the discrete causal set program. Assigning a fully dynamical geometry to the space of intervals in a growing causal set remains an open research question. The difficulty of this frontier is in maintaining the distinction between primitive relations and derived geometry. We cannot smuggle a metric conclusion into an order-theoretic premise.